So more the electronegativity, which makes the haloarene to hold the electron pair of, which makes the partial double bond character over here, like this. Okay, so which makes it partial double bond character. That's why I told you this is not undergoing SN2 or SN1. It is just undergoing SNAR substitution. Okay, so let's start with the preparation of haloarenes. The first preparation is from benzene diazonium salt, which is very important in synthetic organic chemistry, because this is very versatile compound which is used to prepare lot of compounds. How that will look like? Benzene diazonium salt will look like this. Benzene ring with nitrogen and Cl. Okay, so from this, how I can prepare haloarene. So let's me write that as C6H5N2Cl with CuCl and HCl, which is preparing, which will give us C6H5Cl with the elimination of N2 gas and Cl2. Those are the byproducts. This reaction, which is called Sand-Mayer reaction. Again, we will talk about this reaction in amines chapter. This is super important reaction, and the next one is equally important. That is C6H5N2Cl with CuHCl. Any halogens you can replace. You can put HBr also, which will give us C6H5Cl, that is chlorobenzene, along with N2 elimination. So this is called Gattermann reaction. These two reactions, guys, it is super important. How much ever important you want to mention, you can mention it that. Like we said in haloalkanes, I gave you Filkinstein reaction and Schwarz reaction. Those two are very important in case of preparation. Similarly here, Sand-Mayer and Gattermann. These are very important. Ma'am, you have told me chlorine and iodine, fluorine and bromine only. What about fluorines? How we can prepare fluorines? We can prepare fluorines from the same benzene diazonium salt with the special reagent, that is HBF4, hydrofluoric acid, which will give us C6H5EF. This reaction is called Ball-Schiemann reaction. I told you this benzene diazonium chloride, each one of these reactions, each one of this synthesis is super important. The question can be asked in any part, because this is coming under halo chapter also, and as well as amines chapter also. What about iodines? Yes, we can prepare it from benzene diazonium chloride. What not? Potassium iodide, presence of heat, it is producing C6H5 I. Okay. Only benzene diazonium will give haloarenes? No. We can prepare it using halogenation method also. This comes under electrophilic substitution. You remember in hydrocarbons chapter I told you about how the electrophilic substitution happens. What are the groups directing where? And we have discussed pretty much all in electrophilic substitution. The simple substitution you can remember, that is C6H5 reacting with chlorine or bromine or iodine to give C6H5Cl, if that is reacting with Br2 with FeBr3. We should take any loose acid so that it can facilitates the electrophile formation. Br, and if I am treating it with iodine with HiO3, it is giving us C6H5I. And the next way of producing haloarenes, that is from silver salt. The third preparation, it is C6H5COOAG. You can use any halogen, it can be of Cl or Br, which will produce along with AgX plus CO2. And the fourth method, that is Rastrick process, which involves C6H6, that is benzene. I'm treating it with HCl in the presence of oxygen and CuCl2, which is giving us 2 moles of chlorobenzene along with H2O. This method, which is called the industrial preparation of chlorobenzene, which makes it super important, Rastrick's process. Okay, so what about the chemical properties of haloarenes? First thing first, always the nucleophilic substitution reaction. Nucleophilic substitution. I told you it will not undergo SN1 or SN2. It will undergo SNAR. So for doing SNAR, what that should have? It should have a strong electron withdrawing group in the para position to undergo substitution reaction. And you can take HCl to produce C. What if I'm not having any electron withdrawing group? I want only the reaction of haloarenes with other compounds. Then you have to have a drastic conditions like high temperature and pressure. Say for example, I'm having ARX. So I have to apply 623 Kelvin temperature and 300 atm pressure. As surrounding is 1 atm pressure, imagine 300 atm pressure. How much the pressure is high. Along with aqueous NaOH and HCl, which gives us OH, phenol. This is one of those preparation of phenol which is called House process. And if I'm treating it with ammonia and copper oxide, again 60 atm pressure and 475 Kelvin temperature, it is giving us aniline. Similarly, if I'm treating this with copper cyanide with 475 Kelvin pressure, presence of pyridine as a catalyst, it is going to give you cyanobenzene. The presence of electron withdrawing groups such as nitro, cyanome at ortho position or para position, which will increase this kind of substitutions, nucleophilic substitutions, as we told earlier. But if you are using the drastic conditions of high temperature and pressure also, you can achieve it. The next thing, that is electrophilic aromatic substitution. Electrophilic aromatic substitutions. Let's say I'm taking halo or chloro, which will be the electrophile RCO, correct? And presence of Lewis acid to make it electrophile, which will produce ortho and para substituted product, which is like this and like this, ortho and para substituted product. Similarly, if I am treating it with Cl2 with FeCl3, it will again give ortho and para substituted dichloro products, because already I am having chlorine, it will give you dichloro product. Then if I am treating with nitro as an electrophile, then again ortho and para substituted nitrochloro benzene. Then finally, if I want sulfonation, you can go with H2SO4, fuming H2SO4, or if I am having a reagent like this, CCl3 CHO with H2SO4. This will create a very interesting product which is called as DDT, that is having a very good application. It was having a very good application in agriculture field. It is producing DDT. What is that, ma'am? Which is 2,2 bis parochlorophenyl 1,1,1 trichloroethane. That is DDT. Okay, so we have seen the electrophilic aromatic substitutions, and the next thing is reaction with metal. Let's say I'm taking bromobenzene. I'm treating it with many metals. The first I would take sodium. Sodium with dry ether. Ma'am, yes, that is right. What's reaction you have talking about? No, it's not Wood's reaction. Wood's reaction is only for alkanes. It's not for aryls. Then what is this? It's having the same reagent. Yes, this reaction is called fitting reaction. For example, it will produce as diphenyl or biphenyl, which means the higher order of arenes. This is called fitting reaction. Then, if I am treating it with sodium, it's CH3Cl and dry ether. You can see here I am having haloalkane also and arene also. So which means it will produce a product like this. This reaction is Wood's fitting reaction. The combination of two. Then the next reaction, that is magnesium with THF, that is a solvent, tetrahydrofuran, which will produce in the Grignard reagent ArMgX. If I am treating it with nickel aluminium with NaOH, it is giving us benzene. So these are the reactions of haloarenes. Please do check it out, the uses also. I'm telling you, it is there in your book. Ferroin 12, which is one of the most common ferroins which is in industrial use. And chloroform, you know that very well. Carbon tetrachloride, it is used as a fire extinguisher. And if we are inhaling more amount of this methylene chloride, which will cause the dizziness, nausea, numbness too. So the major use of chloroform is the production of the ferroin refrigerant. So uses also you have to give more importance. The questions can be asked from uses also. Okay, so please solve more questions attached with this in the description, and let me know if you are having any doubts in it. Practice more questions. Thank you.